You know, at the very heart of our reality, there's a disconnect, a strange conflict between the predictable, clockwork universe we think we see and this weird, fuzzy, uncertain world that's hiding underneath it all. So today, we're going to dig into that conflict and try to find the bridge that connects them.
And to guide us on this little journey, we're turning to a real classic, R. Schonker's Principles of Quantum Mechanics. We're diving right into Chapter 6, the classical limit, to figure out just how our everyday world manages to emerge from that quantum fog.
Okay, so this brings us to the big mystery, right? Quantum mechanics tells us that on the tiniest scales, particles are just a blur of probabilities. An electron isn't in one specific place, it just has a chance of being in a whole bunch of them. So if a baseball is nothing more than a giant collection of these particles, why does a home run trace this perfect, predictable arc instead of just, well, dissolving into a cloud of maybes?
To get to the bottom of this, we've got to set the stage. It's really a tale of two worlds, and they're governed by two sets of rules that just seem totally incompatible with each other.
So on one hand, you've got the world of classical mechanics, Newton's world. It's totally deterministic. If you know exactly where a ball is and how fast it's going, you can predict its entire future, no problem. But then on the other hand, you have the quantum realm, and it's all about probabilities. A particle is described by a wave of possibilities, and there's this fundamental uncertainty that you can just never, ever escape.
So, how in the world do we get from the quantum to the classical? How does this solid, predictable world we live in just pop out of this bizarre, uncertain quantum soup? Are they totally separate realities, or is one just a supersized version of the other? Well, it turns out the answer lies in this really beautiful, elegant piece of theoretical physics that basically acts as a bridge between these two worlds, and it's called Ehrenfest's theorem.
Think of it like this. It's our Rosetta Stone. It's the key to the translation. Now, it doesn't say that a quantum particle behaves classically. Not at all. Instead, it shows something much cooler. That the average behavior of a quantum particle, what physicists call its expectation value, evolves in a way that looks suspiciously familiar.
And here it is, the mathematical heart of that bridge. Now, don't worry, we're not going to get lost in the symbols here. The important thing is what this equation does. It's a game changer. It connects the rate of change of the average of some quantum property like its position or its momentum to the fundamental quantum laws of motion. It's the engine that drives this whole transition from the quantum world to the classical one.
So, what actually happens when we use this thing? When we apply it to something we can all picture, like the position and momentum of a particle? Well, when you run the numbers, something pretty amazing happens.
This is just fantastic. It lays the connection bare. On the left, you've got the quantum result, how the average position and average momentum change over time. And on the right, you've got the classic laws for the exact position and momentum. I mean, look at them. They're structurally identical. The quantum world, when you average it out, seems to play by classical rules.
Okay, I know what you're thinking. This looks way too good to be true, right? If the equations are basically the same, then why isn't the world just quantum all the way up? What's the catch? Well, the catch is hidden in those little angle brackets. Those brackets mean average. Quantum mechanics predicts how probabilities and averages evolve, not the exact pinpoint values of the classical world.
And that brings us right back to our baseball. We still need to figure out why, for big things like a baseball, the difference between the average value and the exact value just completely disappears. Why don't baseballs, poof, and quantum tunnel right through the bat?
The entire classical world we see, it all comes down to this one single, incredibly powerful approximation. All it says is that the average of the force acting on a quantum particle is almost exactly the same as the force at the average position of that particle. When that one little condition is true, the quantum equations for averages magically turn into the classical equations for exact values.
All right, let's break this down step by step. A quantum particle isn't really a dot. It's more like a spread-out wave packet, a little blip of probability. So it feels the average force across its entire quantum fuzziness. But a classical particle, we imagine it as a single point, feeling the force right at that one spot. The two descriptions only become the same thing if the force is basically constant across the tiny, tiny size of that wave packet. And for a huge object like a baseball, yeah, that condition is met perfectly.
And just how small are we really talking about here? It's mind-boggling. Schenker points out that a typical quantum wave packet is on the order of 10 to the minus 13 centimeters. I mean, that's 100,000th the size of one single atom. Over a distance that ridiculously small, any big force field, like gravity pulling on a baseball, is perfectly uniform. The average of the force is the force at the average position. The approximation isn't just good, it's as close to perfect as you can get.
So all of this, it leads us to a pretty profound conclusion. The classical world, it isn't real. Not in the way we thought it was. It's an illusion. A very, very convincing one, but an illusion nonetheless.
And Shanker just nails it in the book with this line. Once we have bitten the quantum apple, our loss of innocence is permanent. Once you see the fuzzy, probabilistic reality that's underneath everything, you just can't unsee it. That deterministic clockwork universe, it's gone for good.
So let's put all the pieces together. What's the big takeaway here? Well, first, the classical world isn't some fundamental law of nature. It's just something that emerges when you get to really big scales. Second, that predictable path of a baseball isn't proof of determinism. It's just the result of probabilities that are so close to 100% they might as well be certain. And finally, our entire reality is just the macroscopic average of a seething, uncertain quantum world bubbling away just beneath the surface.
And that just leaves us with one final, kind of mind-bending thought to chew on. The solid, predictable world you see all around you, it isn't the true foundation of reality. It's just the universe's best and most convincing approximation. It's what you get when you zoom way out from the quantum ghost in the machine. And it really makes you wonder, what other illusions are we living inside?